When students come to investigate inductance, they will have studied resistance and capacitance beforehand. They will know that the physical value of a resistor is equal to the slope of the voltage current graph. They will also know that the physical value of a capacitor is equal to the slope of a QV graph. And we would like to do something similar for inductance. I have a board and an air-cored inductor. It says on this inductor that its value is 0.5 henries. The board has two AA cells and we can select one or both. There is a path here that we're going to follow. I can close the switch and the current would flow down to here, through my coil and back again, down through the resistor and back to the negative of the terminal of the battery. I have three terminals here which will connect to our Alba data logger. The top one here gives positive voltage. This is a ground, and this voltage here between there and ground gives us a voltage across the resistor. Between the top and ground gives us a voltage right across the two cells. If I subtract the voltage across the resistor away from this one, I am left with the voltage across the inductor. We're not using this switch just now. The diode is in to protect the interface from any spikes. Let's launch the Alba software. We're going to load an application, and it's a physics application and it's called Inductors, the I by dt it switch on. Okay. As usual, the information about the investigation is given to us here. We can go through, and there's our circuit diagram. This is what you saw on the board. We measure the voltage across here. Knowing the value of the resistance, we calculate the current. Subtract this voltage away from the voltage of the top rail to ground, and we're left with the voltage across the inductor. Let's wire up the circuit. First, we'll connect our air-cored inductor. And we'll connect that little wire and the diode across the coil to protect it. And we need to connect the voltages, measure the voltages at the various points. So we need the wires to go over to our data logger into channel 1, that's the top rail, the bottom rail, the ground, and the midpoint into channel 2. That's the circuit connected, and that's our data logger. All we have to do now is to run the software. Start our experiment. Go. Given a choice of air core or iron core, we are on air core, and the difference between these two is simply we need a faster sample rate for the air core coil. Okay. Our graphs are set up for us, current against time and the voltage induced across the inductor against time. The value of the resistor on our board is 430 ohms. And it's saying to hold down the switch A, and we have our graphs. Notice that as the current is changing rapidly, we've got induced voltage, and the rate of change is less here, and the value of the induced voltage is less. we notice also that the value of the induced voltage across this inductor doesn't come to the zero value, even though the current is not changing. And the reason for that is simply that we have a real world inductor. It's not a perfect inductor. Our inductor has resistance. So we could take this current and the current here and the voltage here and calculate what that resistance is. And we could then think upon our inductor as, we could think upon it in 2 bits. One is a perfect inductor in series with a resistor. So if we now look at the table of results that we have for this experiment, we'll go to the beginning of the experiment, so we'll scroll up to the top. Here is our time increasing. We have got the voltage across this real world inductor. So we could again, as I say, think about this as in 2 bits. 1 bit is the voltage across a perfect inductor, and the other bit is the voltage across the resistance of the windings of the inductor. Our program has given us values of current, and we calculate the resistance from these n values that we saw in the graph over here, this part here and here. And if we take the current, multiply the resistance, we will get the voltage across the windings of that inductor. And if we subtract that voltage away from the voltage across the real world inductor, we'll be left with the voltage across the perfect ideal inductor. And we've done that using these 2 columns the whole way down our sampling. If we take the time and we take change in time, and we have a change in, the change in time and change in current values, and we can get from that the change in current divided by the change in time. This has all been done for us behind the scenes in the software. We have a di by dt, a change in current divided by change in time. Taking these points. So I now have a table that contains the rate of change of current with time and the induced voltage across this perfect inductor. So I'm going to select these 2 columns, and with my third click, get a graph. Let's work with this graph. The first thing we're going to do is swap axes. To do that, I go here, and you will notice that we've got that option on the first screen. We can swap axes, and that's it swapped. I would like to see the data points, so I'm going to draw the symbols, and I don't want to connect the points with a line. I'll have crosses, and I'll have nice small crosses, and I'll say OK. That's my graph. Let's fit a line to this graph. Graph close. Best fit line. Let's make that just a little bigger. It's a lovely straight line through the origin. The equation of the line is given in the form y is equal to c plus mx, and the m in here says 0.491. 0.49. We have a 0.5 Henry coil, and we have a gradient of the line which is 0.49. We now have something comparable with Ohm's law, slope of a voltage current graph is the value of the resistance, QV graph giving the value of capacitance, and an induced voltage against rate of change of current graph being the value of the inductor. Further information on the program can be obtained on the DJB website at www.djb.co.uk. Thank you.